Welcome everybody to a video about uncertainties, and we're going to use our experiment from the other day where we dropped something from the third floor stairwell. The first thing we're going to do is we're going to identify anything that could have gone wrong during a lab that would alter our data. The first place we could start is obvious with the timing with the stopwatches. There is no doubt some uncertainty with the timing. Another thing that may have gone wrong or may have altered our data was how well I measured the height of the stairs. You can't assume that that's perfect. There was also me dropping from the exact location where I was supposed to, from 9.2 meters above the ground. There's also the possibility that I may have dropped at the wrong time. I know I said drop, but I may not have dropped at that time. And of course, there's air resistance at the end. Now notice here, all I've done is give a brief statement of all the things that could have altered the experiments. There's no paragraphs here, no sentences, just short statements. Now what we're going to do is we're going to move on to the qualitative part. Now in the qualitative part, your goal is to simply say how these things affect the results of our experiment. The purpose of this experiment was to solve for the acceleration due to gravity. So in the end, you must say how each of these affects the acceleration due to gravity. It can only affect the data that we collect, in this case, time or distance. And then we must say how that affects the acceleration due to gravity. Now, if you remember, we algebraically solved for acceleration and got an expression that said the acceleration is 2 delta d over t squared. Now, this can be very useful when trying to see how it affects the results. For example, let's say we timed too much. That would increase the delta t, which would make the acceleration seem smaller. What if you measured too far? That would increase your delta d, which makes the acceleration seem larger. Maybe I dropped from too low a spot. That would decrease our delta d and make the acceleration seem smaller. I could have dropped too soon, which would decrease the delta t and make the acceleration seem larger. And air resistance would most definitely increase the time, which would then make the acceleration seem smaller. So here, again, all we did was focus on how it affects the results of the experiment. You don't have to say vice versa. You just have to take a side. It doesn't matter which, time too much or time too little. It doesn't matter. Just choose a side and show that you understand how it affects the results. Now, when you move on from here, you're going to the quantitative part. In the quantitative part, you have to make up some reasonable amount you could be off by and divide by the appropriate number. This way we can find a percent error and then take our weakest link to redo calculations to find an acceptable range of possible answers. So in this case, I'm starting with plus or minus 0.2 seconds with the stopwatch. Over our time, I don't remember what it was, so I'm making up 1.28 seconds. And I'm going to multiply that by 100 so that I can get a percent error of, using a calculator, 15.6%. Now measuring the height, I'm going to say I was off by about 5 centimeters at the most. It needs to be a reasonable number. And again, I made it up. Just make sure it's reasonable. Finding the percent error for this, we see that it's really not a lot. It's only about 0.54%. Again, I could have dropped from the wrong location. I'm giving myself plus or minus 0.1 meters of hand movement. That would lead to a percent error of about 1.09%. Dropping at the correct time, that's a guaranteed 0.1 seconds. I'll help you with that in class. Timing is always going to be given. There we have a percent error of 7.81%. Air resistance would increase the time it takes to hit the ground. I'm saying by about 1/10 of a second because it didn't have much of an effect. In this case, it would be 7.81%. Now, 15.6 is the weakest link, so we know that timing was our biggest uncertainty. Therefore, the time could have been plus or minus 0.2 seconds. What we need to do now is to recalculate for that acceleration. So subbing back in to this magic equation, instead of dividing by 1.28, I'm going to divide by 1.28 plus 0.2 seconds to get an acceleration. Or we could do the same equation, but instead of doing plus 0.2 seconds, we can do 1.28 minus 0.2 seconds. This will give us a range of accelerations based on our largest uncertainty. So that range is going to end up falling between 8.4 meters per second squared and, using a calculator to try and figure this out, negative 15.78 meters per second squared. 9.8 does fall between these two values. So for now, we're going to have to accept the fact that 9.8 is probably the acceleration due to gravity until we create a better experiment with more accurate results. And that's about it for this video. Please know that there are no full-page paragraphs here. You can see how little writing was done. All answers are short and to the point. There's no paragraphs. There's no vice versa. It's very clean and short and to the point. Please make sure yours is as well. So I hope this was helpful in any way, shape, or form. If you ever want to get some help on uncertainties, please always attempt it on your own first, and then stop by my room and we'll talk it over. Thanks.